Welcome back to our series on electricity and magnetism. In this episode, we're going to look at charges in an electric field. First, we'll look at a point charge in an electric field and the impact the electric field has on it. We're going to first consider a uniform electric field. So these are going to represent the field lines. Because it's uniform, they will be parallel. That is, their density won't increase or decrease, indicating that everywhere in the field, the electric field has the same magnitude. Now, if I put a charged particle here, we'll indicate first a proton. Well, a proton has a positive charge, and of course, field lines actually point in the direction of force on a positive particle within the field. That's sort of how we define the polarity of an electric field, is an electric field always points in the direction that a force would be exerted on a positive charge. So that means this positive particle, this proton, would feel a force in that direction, matching the field lines. But how big is that force? Well, ordinarily we would use Coulomb's law to calculate the force between one charged particle and another. But of course, there's no charge that's creating this field. There's just the field itself. And from here on out, we're going to see a lot of disembodied fields, that is, fields that don't appear to have a source. Up to this point, all of our fields have had a source of central charge. But we're going to sort of divorce ourselves from that model so that we can look at fields that are actually separated from the charges that cause them. That creates the difficulty, though. How do we account for the force on this charged particle? Well, recall that we got our equation for the electric field by actually taking the Coulomb force and dividing out the second charge, in this case, the charge that's placed in this field. Well, we can simply turn this equation back around and say that the force on any charged particle is due to the size of that charged particle times the field that it's sitting in. And notice that means the direction of the field and the direction of the force will be the same. That's what tells me that for this proton, it will be directed in that direction in the field. Now, of course, because there's a force on it, and Newton's second law says forces cause acceleration if they're unbalanced, I know that this force could conceivably lead to an acceleration. It could actually change the velocity of the proton over time. If the proton had some initial velocity, then together with this acceleration, I might have a complex two-dimensional motion. But all that is kinematics and dynamics, which we will leave for later. For now, we're just interested in the idea that there's a Coulomb force on a particle in an electric field. Even though there aren't two charges interacting, the charged particle interacts directly with the field. Okay, second, we want to look at the performance of a dipole within an electric field. So let's look at that. Once again, I'm going to need a uniform electric field. You may well ask, what happens when the field is non-uniform? And of course, if the field's non-uniform, the same thing will happen, but instead of the force on it being constant, the force will be proportional to the field. So a decreasing field would produce a decreasing force, and an increasing field would produce an increasing force. The actual calculations of those are a little bit beyond the scope of the course. Okay, so here is our second electric field. Once again, it's uniform and pushing to the right. What I'm interested then now is placing a dipole in this field. So the dipole I'll place here. We'll put the positive and negative parts of it here and here. Now, the distance between them is known as d, so I'm going to mark the center, and of course, above and below that center are lengths d over 2. We're going to need those lengths in just a moment. Now let's consider, as a result of it being a dipole with positive q at one end and negative q at the other, it will have zero net force on it. There'll be a rightward force aligned with the field on the positive particle, which will pull the positive particle this way. But equal in magnitude and opposite direction, the negative particle will actually be drawn against the field. Because field lines are always drawn from plus to minus, the minus particle will feel a repulsion from the tips of the arrow and an attraction to the ends of the arrow. So what we're going to end up with is the negative particle pulled to the left with a force that's equal and opposite to the force on the right. Let's draw in those two forces. So the negative particle will experience an F going this way, and the positive particle will experience an F going this way. When I add those two together, of course, from a purely rectangular sense, the forces cancel. There's a rightward and a leftward force, so the net force is zero. But this particle, this dipole, will be able to rotate around its center. So it will have a torque on it, and its motion will be rotational, at least for a little while. Now let me mark the the moment, the electrical moment of the dipole. Remember, the moment points in this direction. It has the vector magnitude p, which is equal to the size of the charge at each end times the length of the distance between it. And it always points from plus to minus. Now you'll notice that that p is not aligned with the field. In order for these forces to act, they're going to twist it around until the dipole points against the field. As it should, after all. If this points towards the negative particles, then the negative particles should be repelled from it. And if this points away from the positive particles, then this should be repelled away from it. And so the dipole will turn until it lies horizontally with its dipole moment pointing anti-parallel to the field. When it does that, it will be in its equilibrium position and the torque on it will disappear. Well, as with all torques, let's go ahead and calculate its magnitude. The magnitude of a torque isn't too bad. What we need are two things. We need the radius from the center perpendicular to the force, and we need the magnitude of the force. So in order to calculate torque, the torque is going to be equal to the size of the radius, which is d over 2, times the size of the force, which is F. And again, we can put in the same F we did over here. It'll be equal to QE. And then finally, it's going to be also equal to the angle, the sine of the angle, which will be right here. That angle is between the electric field direction and the direction of the dipole moment. And I'll take the sine of that angle, and that will tell me the magnitude of the torque. Now let's break down all these pieces. That's really just the torque on the top particle. If I want the total torque, of course, there's two of them, so I can eliminate the d over 2. So it'll just be df sine theta. And then I can go one more step and plug in that F is equal to QE. So it'll be dQE times the sine of theta. Well, you should recognize something about this right away, and that is that dQ is actually the magnitude of the p vector. It's the magnitude of the moment, the electrical moment of the dipole. And the second thing is that P and E, the sine theta, basically signals that this is a cross product between these two vectors. So that's really the torque. The torque is the cross product of P crossed with E. And so if we have vector designations for each one of those, we can simply take their cross product. And if not, we can always find the magnitude of that torque by determining what dQE times the sine of theta is at any given moment. You'll see that this means the torque is maximum when the sine of theta is 90, and it basically means that the moment will be perpendicular to the field. That's when the force will be maximum. The force is minimized when it's lying anti-parallel to the field and parallel to the field. So it will twist or snap around until it lies so that the angle between them is 180 degrees. And of course, the cosine of 180 is 0, just as the sine of 180 is 0, just as the sine of 0 is 0. So that's how you find the torque in between the dipole in the field and the field. Okay? Well, let's go one more step, which is one thing we want to do is calculate the potential energy that lies in this. It turns out that the dipole has more or less energy in different positions based on its potential. It's very similar to lifting a rock in a gravitational field and then having the potential to let it go. When it's highest in the field, it has a lot of gravitational potential and it decreases its potential all the way down. In a similar way, this dipole has more potential energy in one position versus another. Let's see if we can calculate that. Well, potential energy is U, and it's always equal to the negative of the work, whatever work we have to do on this. And of course, work is just the integral of the force times the displacement. So this equals the integral of the force on it times the displacement, which in this case would be dl or dx, however far it's going to work. It's a dot product because it always has to do with the degree to which the work is in the direction of the displacement. Well, in our case, it's rotational work. So we're going to replace the force by the torque, and we're going to replace dl by d theta. So this will be the integral of the torque d theta. We can even put in our limits. We're only going to calculate the work done for half of it and then know that each half is symmetric. So our limits will be from pi over 2, its maximum value, to 0, which should be its minimum value. Well, when we dump in the torque being equal to q dE sine theta, and we go ahead and perform the integral, here's what we end up with. We end up with negative PE cosine of theta. And that should be recognizable to you too. Taking the magnitude of both the P vector and E vector and multiplying by the cosine theta, that's equivalent to the dot product. So it turns out that potential energy is always equal to the negative of the dot product between the electric dipole moment and the electric field vector. So if you want to calculate the potential energy, you just need to know the angle in between them, or if you happen to have these in unit vector notation, simply take their dot product. Why is it negative? Well, when we consider when we're all the way aligned, so the angle between them is 0, again, this is going to produce the largest possible value. And of course, that's when it will have the greatest potential energy. And because potential energy is the negative of the work, that will produce the largest magnitude. When we flip around, it'll have the minimum amount of potential energy when P is actually anti-parallel to the field, and it will have the medium amount in the middle. Actually, the medium amount here qualifies as 0 because remember, potential energy has a scale that's set by us. In this case, the scale is +1 is the maximum, the product of P and E, 0 is the medium value, and -1 is the minimum value. So that's how we'd calculate the potential energy of the dipole in the field. The behavior of charges in electric fields is pretty consistent. As long as those electric fields are constant, the formulas are pretty straightforward, and this is an easy concept. It does become more difficult as the fields become variable, but of course the mathematics for that is going to be a little bit beyond us. What do we look at next? Well, it's time for us finally to look at a better way to calculate electric field from charge distributions, and that we're going to pick up in our next video by defining a new concept called flux.